Okay, so hi everybody, and welcome back. Today what we're going to be doing is starting a new chapter. That's chapter 20 of the textbook. And the topic here is entropy and the second law of thermodynamics. So let's get into this. We'll introduce the topic by thinking about a question. I want you guys to think about this. Consider the following hypothetical process. Block 1, initially at 300 degrees Celsius, that's this one over here on the left, is in contact with block 2, initially at 600 degrees Celsius. That's the one over here on the right. Suddenly, 1,000 joules of energy flows out of block 1 into block 2. In doing so, this increases the temperature of block 2. So now we're at 601 degrees Celsius, and it decreases the temperature of block 1. Now this one is at 299 degrees Celsius. So I think we know that this is not something that would happen, right? Heat doesn't tend to flow from cold objects to hot objects. But what I want you to think about is, does this violate the first law of thermodynamics? Does this violate conservation of energy? So think about it for a minute, pause the video, and see what you come up with. Okay, so the answer to this is no. It doesn't violate conservation of energy. It doesn't violate the first law of thermodynamics because all that's happening is we're taking 1,000 joules of energy, which was initially contained in this cold object, and it's just moving over here to this hot object. So energy moving from one place to another doesn't violate the first law because you're not creating energy out of nothing. You're not destroying energy. Energy is conserved, right? It's just moving from one place to another. That's totally fine. But we know that this can't happen, okay? Heat doesn't flow from cold to hot. It flows from hot to cold. So what would really happen is that heat would be flowing from this hot object to the cold object. The hot object would be cooling off. The temperature would be decreasing. And this object, the cold one, would be increasing in temperature until the point where they reach the same temperature. So what's going on here is heat is sort of flowing the wrong way. But the first law of thermodynamics is not enough to say that heat has to flow one way and not the other. So we need a different law of thermodynamics, a new law of thermodynamics, to explain why heat flows from hot to cold objects, but not the other way. Okay, so that brings us to the concept of entropy. So like in the previous example that we looked at, there are many different processes that happen in the real world that never happen in reverse. So they only seem to happen one way, but not the other way. Let me give you some examples. Let's say you have a wine glass and it shatters. So if you watched a video of this happening backwards, where all these shards of glass come together and they form an entire wine glass, they come back together, we would know that something's wrong. We know that's not what happens, okay? So once the glass shatters, it doesn't reassemble itself back into a full wine glass, okay? That doesn't happen in reverse. Another example would be a sliding block that slides across a table and it's brought to a stop by friction. So what's really happening when an object that's sliding across a table is brought to a stop by friction? Well, it initially has some kinetic energy because it's sliding this way, but that is converted to internal energy because as friction does its work, the atoms that make up the table and the underside of the block, they actually start jiggling around faster and it heats up the surfaces. We're converting kinetic energy into internal energy, in other words. What doesn't happen is you never have a block that's just at rest on the table, and then some of the internal energy of the molecules and atoms that make up the table go into the block and then cause it to start sliding, right? That never happens. So in other words, this is a process that, again, we don't see happen in reverse. Another example would be you put an ice cube on a table and heat flows into the ice cube from the surrounding air and from the table, and it causes it to melt. So what you don't see is a puddle of water on a table that assembles itself into a frozen ice cube, right? Again, that's not something that happens in reverse. So for all of these different examples and more, we need the concept of entropy and the second law of thermodynamics, which is about entropy, to explain why certain processes are irreversible. They only happen one way, and they don't happen in reverse. So we're going to build up a picture of entropy and the second law of thermodynamics, but we're going to start with something that seems unrelated, but I promise you this will all come together at the end, which is heat engines and refrigerators. Okay, so let's start with heat engines. Now, a heat engine, for our purposes, is just anything that takes heat and converts it to mechanical work. So the input, what you put into the heat engine, is Q, and what you get out, the result of that heat, is mechanical work, okay, W. So in other words, the engine is performing mechanical work for you if you put some heat into it. Now, there are many different examples of this. One example that we encounter in our everyday lives is the internal combustion engine. That's the type of engine you'd find in a typical car. I know that now some cars are electric powered, but for the most part, we still run on internal combustion engines in our cars. Now, we also have diesel engines. These are things that you would find in trains, some trains, and larger trucks. And also steam turbines, which are what you would find in a power plant. Most of our electrical grid, in other words, is powered by heat engines ultimately. So the invention of heat engines is a huge deal in human history because it completely changed the way we live. Now, it's hard to pin down an exact date, but the first heat engines were developed sometime around the early 1700s. So they've been around for about 300 years or so. And prior to heat engines, it was very hard to travel across land. Okay, but now we have things like cars and trains. Also, with heat engines, we can build things in a way that we never could before, and we can manufacture things in a way that we never could before. So it completely changed the way we live after the invention of heat engines. Okay, so with that said, let's define something called the working substance. So the working substance in our heat engine is what is actually doing the work, what is actually performing the work. And for our purposes, we will always assume that the working substance is some type of ideal gas, okay? Now, typically, the way the work is going to be performed is your gas is moving a piston. It's pushing against a piston and moving it back and forth. So the basic picture you should have in your head for a heat engine is there's some source of heat. That heat flows into the working substance, which again is just some ideal gas. That gas pushes against a piston and it can move the piston back and forth. That's the mechanical work we're talking about. And of course, the piston moving back and forth can be used to maybe rotate a wheel. If you want to get rotational motion out of that, that's a pretty simple next step you can take. Okay, so one important thing we need to realize about heat engines is we want them to keep going. We want them not just to sort of push a piston out and then stop. We want the piston to keep moving back and forth in a cycle so that we can continuously get work out of it, okay? So a heat engine operates in a cycle. We have a series of different processes that the gas, the working substance, is undergoing. So we're combining things like isothermal, adiabatic, isobaric, and so on that we learned about in the last chapter. And to give you an idea of what this looks like on a PV diagram when we have a cycle, you start at some point on the PV diagram, you undergo a series of processes, but it's really important that you always come back to where you started so that you can repeat the cycle again. So the cycle can just keep happening over and over again, and you can keep getting work out of the gas. So what that would look like is something like this. So notice how the system again follows that cycle and returns to its initial state. Okay, now what we have in our heads is a piston, which is being pushed up and down by an ideal gas. And what we can do is convert that linear up and down motion into rotational motion using something called a crankshaft. So let me show you an animation of that happening. Okay, so again, the piston is moving up and down. It's driven by the ideal gas. And then we convert that linear motion into rotational motion using a crankshaft so we can get the wheels of your car spinning or anything else we want rotating to start rotating. Okay. So I have a question for you guys to try out. Suppose we have a working substance of a heat engine that undergoes the cycle shown in this PV diagram. I want you to think about what the total work done by the gas in one cycle is. So you don't have to calculate a number. I just want to know if it's positive or negative. Is the work done by the gas positive or negative for this cycle shown here? And then as a follow-up, if the cycle were run in reverse, would the total work be positive or negative? So pause the video, try to work this out, and then we'll go through it together. Okay, so to work this out, let's just recall that work done by a gas is the integral P dV, which we can interpret as the area under the curve in a PV diagram. Okay, so what we'll have to do if we want the work for one complete cycle is to break the cycle up into the 4 different processes that we see here. So first, we have the work from A to B. Then we have the work that the gas does as we go from B to C. Then the work as we go from C to D. And then finally, the work as we go from D to A. So that completes the cycle. We come right back to where we started, so that's what we want to calculate. So for each one of these, let's try to see what we can figure out about the work. So if we go from A to B, what we're dealing with is a gas expanding. So the volume increases, and we know that if the gas is expanding, that the work is going to be positive. If we go from B to C, the volume doesn't change. And we know that in a constant volume process, there's no work being done. Okay, if we go from C to D, the gas is contracting. And we know that when the volume decreases in a contraction of a gas, that involves negative work. And then finally, if we go from D to A, the volume is once again constant, which means there's no work being done. So right away, we can take the 4 different terms and cross 2 of them out, WBC and WDA. We just have to worry about the other 2. So we have one positive term and one negative term, but we can compare them in terms of absolute value. Okay, so ask yourself, just in terms of absolute value, which one of these works is bigger? Is it WAB or WCD? And you can just look at the diagram and immediately conclude it's WAB. There's more area under this curve that takes us from A to B than there is under this curve that takes us from C to D, which I'll show right here. So that's why we can conclude there's more work. So for the cycle then, think of it like this. We have a positive but bigger absolute value, and then a negative with a smaller absolute value, which is going to give us something positive, greater than 0. So positive work for that cycle. Now, if we run the cycle in reverse, so here I want you to imagine that we basically flip all the arrows around. Okay, so point this one the other way, and this one too, and this one. So now we're going from A to D to start off. Well, there's still no work there. And then we're going from D to C. So the gas is now expanding along the curve that takes you from D to C. So that's positive work. Okay, now we go from C to B. Again, that's going to be at constant volume. So 0 work. And then finally, we go from B to A, and that involves the gas contracting to a smaller volume. So there's negative work. But it's still true that the absolute value of the work from A to B is bigger than the absolute value of the work from C to D, right? That's still true in terms of the area under the curve. So for the cycle reversed, we have now a negative term with a bigger absolute value. Okay, that's this one. Plus a positive term with a smaller absolute value, which of course is going to turn out to be something negative or less than 0. So run the cycle in reverse, and it's actually negative work being done by the gas. Okay, so let's take a look at a heat engine schematic. This is a picture, a very simplified picture of what's going on in a heat engine, and it ignores a lot of the details, but it still captures a lot of really important things that we want to focus on in terms of the physics. So in particular, a heat engine schematic tells you overall what is happening over one engine cycle. Again, ignoring the details in between. So this picture, this heat engine schematic, is something we'll come back to time and time again. It's a really useful way of looking at a heat engine. Okay, so one thing that has to happen during the engine cycle at some point is that your working substance, the gas, has to take in some heat from the outside. So heat has to flow into the gas from the outside. The way we show that on our heat engine schematic is we say, look, there's some high temperature region, TH. We call this the hot reservoir, and the temperature of it is TH. Some heat flows from that hot region into the gas. So that heat flow we call QH. Okay, also, we want the gas to be doing some kind of work, so we show that the gas is doing work with a little arrow like this, labeled W, letting us know that the gas is doing work on its environment, so the output is work. Okay, this third arrow is showing us another sort of heat flow that's happening in the engine cycle. So this is what we call the waste heat or the exhaust heat. Okay, so as we're going to see, inevitably, the engine is going to have to give off some waste heat to the environment, and what we call that is QL. So this heat flow is QL, and it goes from the working substance, the gas, to the environment at a lower temperature. So we call this our cold reservoir, and the temperature is TL. Again, we're going to get a much clearer picture of why we need QH and QL, and we have these two temperatures. But for now, let's just sort of take it and run with it. And what I want to look at in particular is how do we apply conservation of energy? How do we apply the first law of thermodynamics to this engine cycle? So if we do that, and I'll show you where this comes from in a second, we're going to get the absolute value of QH equals the absolute value of W plus the absolute value of QL. So this is the first law applied to an engine cycle. Okay, so the first law for ideal gases, this is something we learned about back in chapter 19, is Q equals W plus delta E internal. So let's apply that to an engine cycle. So after one full engine cycle, remember the gas returns to its initial state. So what we can say about delta E internal is that, well, it's the final value of E internal minus the initial value. But if we start and end at the same exact state, then E internal initial value is the same as E internal final value, and the overall change will be 0 because we, again, just come right back to the same state that we started at. Okay, as far as the heat is concerned, let's break that up into two parts. So we have positive QH, because heat is flowing into the gas at that point. So here, QH, that's flowing into the gas. Then we have a negative heat because QL is the heat that's flowing out of the gas. That's our exhaust heat. So let's put this all together. So we have Q equals W plus delta E internal. But what we did is we broke the heat up into two parts. So we have QH minus QL. And again, I'm using absolute values here just so we don't get confused about the signs. That equals the work. So here, I'll just say the absolute value of the work on this side, because the gas is doing positive work, plus 0 for delta E internal. So then I can write this as QH is equal to W plus QL. So the way you interpret this is, look, at some point, you put some heat into the gas. And what does the gas do as a result? Well, the gas does some work. But that's not all. The gas also has to give off some heat to the environment. It has to give off this exhaust heat, and that's QL. So in terms of what you put in, QH, two things happen. The gas does work, and it also gives off some exhaust heat. That's how you interpret this. Okay, and that brings us to the efficiency of a heat engine. So whenever you encounter this term efficiency, it means different things in different contexts, but generally you can think of it as the ratio of what you get out to what you put in. Okay, so it's the ratio of what you get out to what you put in. For a heat engine, what we're trying to get out, what we're trying to make the engine do is work. And what you have to put in is heat. And in particular, we're talking about QH, because again, QL is just waste heat. So you put in QH, okay, during one engine cycle. So by definition, the efficiency of a heat engine would be work divided by QH. Okay, that's how we define efficiency for a heat engine. So real quick, I just want to show you another way we can express the efficiency of a heat engine. Again, it's work divided by QH. But if we take the first law as it applies to a heat engine cycle, we can see that absolute value QH equals absolute value of work plus absolute value QL. So therefore, I can express the work that my engine is doing over the course of one cycle as QH minus QL, both absolute values, of course. So let's put that into our formula for efficiency. So efficiency, given by epsilon, is QH minus QL divided by QH. So QH over QH is 1, and then we have minus QL over QH. So all I need to know to figure out the efficiency of a heat engine is the two heats QL and QH. Okay, so again, the definition of efficiency, epsilon is equal to W divided by QH. So it's the total work that's output by the engine in one cycle, divided by the heat that you put into the engine in one cycle. So now I want you to think about the expression we just derived. We can rewrite this as 1 minus QL over QH. So it's useful to write it this way sometimes because you just need to know the two heat terms. You don't need to know the work to know the efficiency. And while we're talking about efficiency, let's try to think of what would a perfectly efficient engine look like? Well, perfect efficiency would be epsilon equal to 1. So what that would mean is W and QH are the same thing. The ratio is equal to 1. So every little bit of heat that you put into the engine is converted to work, and none of it is waste heat. Okay, so there's no QL, in other words. So a perfectly efficient engine where epsilon is equal to 1 would involve converting all of the input heat into work, and none of it goes as waste heat. Okay? But as we're going to see, that's just not possible. You can't have a perfectly efficient engine because it would violate the second law of thermodynamics. Okay, and that's something we're going to build up to over the next couple weeks. Okay, so even though we're not quite ready to state the second law of thermodynamics in general, we kind of have a little hint of it in this discussion of heat engines. So what I'm going to tell you about is something called the Kelvin-Planck statement of the second law of thermodynamics. So this was developed by two physicists named Kelvin and Planck, and it goes like this. It's not possible to design a device that operates on a cycle whose sole effect is to take in a given amount of heat and convert all of it to mechanical work. So that would not be possible. And again, that's just another way of saying you can't have an efficiency equal to 1. That's not possible. And the schematic here is showing us what this impossible heat engine would look like. Okay, so we're imagining you take in some heat QH at a high temperature, and then all of that energy that's taken in goes into the gas doing work. Okay, and none of it is exhausted as waste heat. This is not possible. Okay, so let's take a moment to do a practice problem where we get to use the equations we've developed up until this point. So let's imagine we have a 20% efficient car engine that produces 23.0 kilojoules of work during each cycle. How much heat is input every cycle? So what's QH? And how much heat is exhausted, QL, every cycle? If the engine operates at 120 cycles per minute, what is the power output of the engine? So pause the video, try to work these out, and see what you come up with. Once you think you have some answers, come back to the video and we'll go through it together. Okay, so here's what we know. The work from one cycle is 23.0 kilojoules, and the efficiency is 20%, but we want to write this as a decimal, not as a percentage, so it would be 0.200. Okay? Now remember, efficiency, by definition, is work over QH, W divided by QH. So if we want to know QH, just take the work and divide the efficiency. So W divided by epsilon. So that would be 23.0 kilojoules divided by 0.200 for the efficiency. And this works out to 115 kilojoules. Okay, so what this is saying is you put in this much heat, but you only get out this much work. So you get out a lot less work than the heat that you put in. Okay, that's just what it means for an engine not to be perfectly efficient. If we want to find QL, there are a couple different ways we could do it, but let's bring in the other equation we derived. So QH is equal to W plus QL. And if I want to solve for QL, that's going to be QH minus W. So here, for QH, we have 115 kilojoules. And we want to subtract 23 kilojoules, which gives us 92 kilojoules. So that's the waste heat that gets exhausted into the environment. So in fact, most of the heat that we put in is just converted to waste heat. Okay, so for the power output, we're going to start with the fact that every cycle, we have 23.0 kilojoules, or 23.0 times 10 to the third power joules of work being done. So 23.0, 10 to the third joules per cycle is the rate at which the engine is doing work. And that's what it means to talk about the power of the engine, the rate at which the engine is doing work. All we have to do is get this in the right units. And the way we can do that is by taking the information that the engine operates at 120 cycles per minute. So here, 120 cycles every 1 minute is sort of a conversion factor that we can introduce. Cancel out cycles. Now, in every 1 minute, there are 60 seconds, of course. So cancel out minutes. And now the units we have are joules per second. Okay, so this comes out to 46.0 10 to the 3. And remember, a joule per second is equivalent to a watt. So a watt of power is a joule per second. So we have 46.0 10 to the 3 watts. Or we could just say 46.0 kilowatts. That would be the power output of our engine. Okay. So next, let's define something called a reversible process. Now, this is a term that's going to come up a lot throughout the lecture, so it's important we know the definition and we know the terminology before we go any further. And reversible means pretty much what it sounds like. It means you can take a system that undergoes some process and then you can do the process in reverse. But it means a little bit more than that. It means that when you do the reverse process, there's no overall change on the environment. So the system goes back to its starting state and the environment also is not changed when we reverse the process. Okay, so technical definition is a process is reversible if the system can be taken back to its initial state without any change on the environment happening when you do the process in reverse. Okay, so we'll go through some examples of this in a second, but to expand on that a little bit, for a process to be reversible, two things have to hold true. So number one, no friction. You can't have any friction at work in a reversible process because friction basically dissipates energy into the environment. And that energy can't come back just because you do the process backwards, okay? Once, friction does work and dissipates energy to the environment, that energy is not coming back. So we say no friction. Also, the process has to be quasi-static. Remember from the last chapter, that means it happens very, very slowly. And in fact, infinitely slowly, because otherwise the system and the environment will go out of equilibrium. That's not something we want to happen for a reversible process. Okay, so a reversible process is kind of an idealization. Any real process that you would see happening in the real world is not reversible. We would say it's irreversible because There's always going to be some degree of friction. You can't really do things quasi-statically because, again, that would take infinitely long. But it's still a really useful concept because it will really help us understand the limits of what's physically possible. So in other words, one thing we're going to do in this lecture is understand why perfectly efficient engines are not possible. And to get there, we'll have to think a lot about reversible processes. Okay? So here's a question for you guys. I've got 3 examples given below, and for each one of them, I want you to determine whether the process that's being described is reversible or irreversible. Okay, so number 1, a gas in a cylinder moves a piston with no friction as it expands isothermally. Okay, number 2, a gas in a cylinder moves a piston with friction as it expands isothermally. And number 3, a gas in an insulated cylinder expands freely. So what we want to think about here is the piston is moved out so fast that the gas hasn't even begun to expand by the time we stop moving the piston. Okay, so what I want you to do here as you work these out, not only just write down reversible or irreversible, but try to sketch out a picture of the process and how heat is flowing and how maybe work is being done, and allow that to help you come up with your answer, okay? So at this point, pause the video, try to work this out, and then once you think you have answers, come back to the video. Okay, so let's look at each one of these examples, starting with the first one, which is the isothermal expansion with no friction. And it's good to be able to picture the process and visualize what's happening. So we'll draw a little picture. So this is a little cylinder that contains the gas. And this is a piston, which can move in or out as the gas expands or contracts. In this case, we're imagining the piston is moving out because the gas is expanding. But if this is all happening isothermally, that means constant temperature. Remember, in the previous chapter, we said that an isothermal expansion involves the gas connected to a heat bath, which maintains a constant temperature T. That's how this works. So we know that the gas is doing some work because it's expanding. So we'll indicate that as W with an arrow pointing from the gas to the environment. So what we say is the gas is doing work on the environment. And also, there's some heat flow going on. There's heat flowing into the gas from the heat bath. So Q is going to be going from the heat bath to the gas. That's how you should be picturing an isothermal expansion. So heat flows into the gas from a really large system, and then the gas does some work on the environment. And what we will call this is the forward process. We can also look at the reverse process, where we just run that whole scenario backwards. So here's the heat bath once again, here's the piston. And the piston has already expanded out. So we want to move it back to its initial position. So we're going to sort of move the piston inwards. And while we're doing that, we'll notice that now our work arrow is sort of reversing direction. What we mean by that is the environment is now doing work on the gas. Okay? And also, heat is flowing the opposite direction. Now heat is flowing from the gas back into the heat bath. So that arrow for Q is pointing the other way. So notice how, if we do the forward process, and then immediately after that, we do the reverse process, we end up right back where we started. So the gas is right back in its initial state, and there's no overall change on the environment. So here's how that works. In the forward process, some energy went from the heat bath into the gas. In the reverse process, all of that energy just went right back into the heat bath. So again, the heat bath is right back where it started. All the energy that flowed out just flowed back in during the reverse process. When we think about the work, okay, so the gas did some work on the environment. It transferred some energy to the environment in the forward process. In the reverse process, that energy just went right back in. Okay, so everything is exactly back where it started. That's what it means to be reversible. So that's reversible for sure. But now if we look at the case with friction, isothermal expansion with friction, there's a little bit more going on in this picture. So we still have a heat bath, a cylinder containing some gas with a piston that encloses it. And in the forward process, the gas is expanding, so the piston is moving out this way. So this will be the forward process. And just like before, of course, we have some heat flowing from the heat bath into the gas. And the gas is doing some work on its environment. But there's one other thing that's going on that wasn't going on before. There's friction between the piston and the walls of the cylinder, which is generating heat. So friction generates some heat. And we can show that with a little arrow. Basically, some heat flows into the environment because of this friction. So I'll write that as Q friction. Okay? Now, if we reverse that, so the gas is expanded, now the piston is being pushed back in. So we know the work is being done on the gas. So we show the arrow for W going towards the gas, and the arrow for Q is going the other way towards the heat bath. Okay, but think about this. There's still friction as the piston moves. It still generates heat. And that heat is not flowing back the other way. That's still flowing out into the environment. Okay? So, what do? Do we have the same exact state when we do the reverse process? Well, no, because basically we've generated heat that flowed into the environment, and that heat does not come back. Okay, so this is irreversible. Okay, so the third case was what we call the free expansion. And what that looks like is you have a cylinder, there's some gas molecules inside, and they're sealed inside by a piston. And let's draw a little dash line to say that the piston is initially located here. But what we do is we move it out so fast, say it ends up here. So it moves very fast, piston moves fast, so that the gas doesn't even have enough time to respond. So in fact, it leaves a little empty space or a vacuum momentarily, and then sometime later, the gas expands into the new volume. Okay, so the thing about this is the work done by the gas is actually zero. And this is because the gas molecules are never pushing on the piston as it moves out. The gas molecules are not exerting a force on the piston. Okay, so the piston just moves over here, and then the gas molecules expand into the new volume, but they're never pushing on the piston as it moves. So there's no work being done. Okay, so this would be the forward process. The reverse process would be, now we have the gas, it expanded already to this volume. And I want to take it back to the original volume. So what I'm going to have to do is push that piston inwards. Okay? And in doing so, you'll have to do work on the gas. So to push the piston back, you'll have to do some amount of work on the gas. Okay, so this is clearly not reversible because there's a different amount of work in the forward process than in the reverse process. So this is irreversible. And that makes intuitive sense. We know that once a gas expands into this new volume, it's not just going to reverse all on its own without any other changes. So that fits the definition of irreversible. So that takes us to refrigerators and AC units. So for our purposes, we can think of a refrigerator and an air conditioning unit as pretty much the same thing. Obviously, there's some differences in the details of how they're designed, but in terms of the physics, they're pretty much functioning the same way. They do the same sort of thing. So if we have a heat engine where all the different processes that happen can be reversed, well, then we can run the heat engine in reverse as a cooling system, okay? So let's really think about what this means. Instead of the working substance outputting some work, now we're going to have to input some work. So we're going to have to do work on the gas, okay? Now, instead of heat flowing from the hot region to the working substance, it's going to flow the other way. So our QH is going to be going from the working substance, that's the gas, to the hot region. And instead of waste heat being dumped into the cold region, as it would with the heat engine, that's flowing the other way too. Our QL is going from the cold region into the gas, okay? Now, if you think about it, this is exactly how a refrigerator or an AC unit would work. You have to put some work in, so you have to power it somehow. There's going to be a motor of some kind inside of the unit. So work is being done, again, on the gas in that way. And you have a cold region, which in the case of a refrigerator would be the inside of the refrigerator that you're trying to keep cold. Temperature is TL. And you're trying to remove heat from there. So that's what QL is showing you here. There's heat being removed from the cold region. We're keeping it cool by removing heat continuously. But then we have to dump some heat into the hot region, which, if we're talking about a refrigerator, would just be the room around the refrigerator. That temperature would be TH, and there would be QH flowing into that hot region. So you may have noticed, if you ever kind of feel the back of a refrigerator, it feels hot. And that's because there's this QH flowing into the room. That's what we're showing in this diagram. Okay, so the same equation that we derived for heat engines is still going to hold true. QH is going to equal W plus QL. That still holds true. It's just that in our schematic, all of the arrows are reversed. That's what it means to reverse the cycle. Okay, and that brings us to the coefficient of performance. Remember, for heat engines, we had this idea of efficiency, okay? And for a heat engine, that was the ratio of the work to the heat that you put in, so W over QH. Now, when it comes to a refrigerator, we're going to define this in a slightly different way because what we're putting in to the refrigerator is work, right? We're powering it using maybe some kind of electric motor, but the point is the input, what you put in, is work. And what you're trying to get out, what you're trying to get the refrigerator to do is remove heat from the cold region, okay? A good refrigerator is constantly removing heat from the inside. That's QL. So the ratio of QL to W is telling us basically how good of a refrigerator you have. Okay, so the coefficient of performance is defined as QL divided by W. Okay, where QL is the heat removed in one cycle, and W is the work that you have to do during one cycle. So QL, heat removed from the cold reservoir, divided by work done on the gas, the working substance, in one cycle. That's how this is defined. Okay, so the coefficient of performance is defined as QL divided by W. And remember from the first law that QH is equal to QL plus W. So I can write work as QH minus QL. And that goes in the denominator. So we have QL divided by QH minus QL. This is just another way you can write the expression for the coefficient of performance. It's useful because it's completely described in terms of the two heats, QH and QL. If you know those, you can get the coefficient of performance. Okay, so what we just showed is that you can rewrite the coefficient of performance as QL divided by QH minus QL. And again, this is useful because everything is expressed in terms of the heat. And so the next thing to think about is what would it mean to have a perfect refrigerator? So what I mean by a perfect refrigerator is it still removes heat from the cold reservoir, so you still get this QL, but you don't even have to put in any work. So you don't even have to run a motor, you don't have to use any electricity to power the refrigerator. It's just cooling off the inside without any input of work. So if that's what we imagine as a perfect refrigerator, I'm dividing by 0, okay? The work is 0, so technically that would give us an infinite coefficient of performance. So COP going to infinity is kind of what we mean by a perfect refrigerator. But as we're going to see, this is not possible. You cannot have a perfect refrigerator with an infinite coefficient of performance and no work needing to be input to make it operate. And as we'll see, this would violate the second law of thermodynamics. That's why it's not possible. So again, we're not quite ready to state the second law of thermodynamics and see it in general. But again, we're seeing somewhat of a hint as to what the second law of thermodynamics says. So this is called the Clausius statement of the second law of thermodynamics. So this was developed by someone named Rudolf Clausius. And the statement is, it is not possible to design a device that operates on a cycle whose sole effect is to transfer heat from a cold region to a hot region. So again, let's think about this perfect refrigerator with an infinite coefficient of performance. What would that look like if we drew it on a schematic? Well, there's no work. That's what we're assuming. No work has to be input. So all that's happening is you have QL, which is going from the cold region into the gas, into the working substance. And then at the same time, the gas is just dumping that heat into the hot region. So QH is equal to QL whenever we don't have any work. Well, that kind of makes no sense on its face because, of course, heat doesn't just naturally flow from cold regions to hot regions. So we can see there's something wrong with this, okay? We can see that this is not really going to be possible. So this infinite coefficient of performance, this perfect refrigerator where we have no work input, is actually not possible. And we're going to see why as we start to develop the second law of thermodynamics. Okay, so let's take a look at another example. In this example, we're going to imagine that we have a heat engine and we're using that engine to run a refrigerator. So the heat engine is powering the refrigerator. So suppose that a heat engine with an efficiency of 0.450 is being used to power a refrigerator, which has a coefficient of performance of 0.680. How much heat would you need to put into the heat engine? So what would QH for the heat engine have to be if you're going to use the refrigerator to cool off 156 grams of water from 30.5 degrees Celsius to 11.0 degrees Celsius. We're going to assume that all of the heat we remove from the refrigerator goes into cooling the water. Okay, so let's work this one out. Okay, so to understand what's going on here, it's going to be really useful to draw a picture. There are a lot of different types of energy that are moving around in this problem, so it's good to know how to keep track of them. We'll start by drawing a schematic for the heat engine. So remember how this works. We have QH coming in, and then as a result, the engine does some work. So W is going out. And also, it's just inevitable that you're going to have some waste heat. So we'll call that QL. Okay, we also have a refrigerator in this problem. So we'll draw the schematic for that. So when it comes to a refrigerator, work has to be put in. So I'll have a W going into the refrigerator, and I'll put a little prime on this so we can keep it separate from the W for the engine. Similarly, we're going to have QL going the other way. So here, I'll write that as QL prime, again, to keep it separate from the other QL. Now, this is the inside of the refrigerator. So what this is showing is heat is being removed from the inside of the refrigerator. And then we have QH, which is being dumped into the outside of the refrigerator, so just the surrounding air in the room. But again, we'll say that's QH prime, just to keep it separate. And that's what you should be visualizing in terms of the energy flowing around. Okay, so a few other things to note. What is the efficiency of the engine? How is that defined? Well, epsilon is, by definition, W divided by QH. The coefficient of performance of the refrigerator. Okay, this is defined as, so we have COP is equal to QL, but again, I'm using the prime notation from the refrigerator, so that would be QL prime divided by W prime. Okay, another thing that's really important to realize here is that since the engine is powering the refrigerator, okay, the work that's output by the engine goes into the refrigerator. So W is equal to W prime. That's what it means for the engine to power the refrigerator. Okay? Okay. So we know something about the heat removed from the inside of the refrigerator. Because again, this is the heat that cools the water off. Okay, so here, QL prime, that's the heat removed from the inside of the refrigerator. If that's cooling the water off, then it will equal MC delta T. In other words, the mass of the water times the specific heat times the temperature change. Okay, and we can actually calculate that. QL prime, how much water do we have? Well, 0.156 kilograms. Specific heat of liquid water is 4,186 joules per kilogram degrees Celsius. And then we have the temperature change. The final temperature is 11 degrees Celsius. That's what we cooled the water off to. The initial is 30.5. So this comes out to actually something negative, minus 1.273 times 10 to the 4 joules. The negative sign just means the heat must be leaving the water in order to cool it off, okay? All right, so the next thing we can do is, again, use the fact that the work done by the engine is the work that goes into the refrigerator. And if we go to the definition of coefficient of performance up here, okay, W prime is the same as QL prime over the coefficient of performance. So we have absolute value, so just make that positive, 1.273, 10 to the 4 joules over the coefficient of performance, which is 0.680. And this works out to 1.872, 10 to the 4 joules. Okay, so just to be clear, this is how much work is done on the gas in the refrigerator, which is the same as the work done by the gas in the engine. That's the amount of energy. Okay, so the last thing we can do is look at the definition of efficiency. And if we want to solve for QH, that's going to be the work W divided by the efficiency, W divided by epsilon. So we just found the work, that's 1.872, 10 to the 4 joules, divided by the efficiency, which is 0.450. Okay, so this comes out to 4.186, 10 to the 4 joules. So remember, what we just calculated is this, QH. You have to put this much heat into your engine if that's going to power a refrigerator that cools the water off in the way that we showed. So we're only removing here 1.27 10 to the 4 joules of energy in cooling off the water, but you have to put in much, much more than that into the engine to get that to work, because not everything is perfectly efficient. Okay, so the next type of device that I want us to take a look at is a heat pump. Now, a heat pump is pretty much the same thing as a refrigerator if we're just drawing a schematic of it. It operates on the same principle, but the difference is the goal of a heat pump is to bring heat into the hot reservoir. So let's take a look at the schematic. So we have a cold region, the temperature is TL. We have a hot region, the temperature is TH. And then we have a working substance, which is typically going to be a gas of some kind. And just like for a refrigerator, we have QL flowing out of the out of the cold region into the working substance. We have QH flowing out of the working substance into the hot region. And then we're doing some work in this process on the gas. But this time, you should imagine we're using this to heat up a house, okay? So you're heating up a house on a cold day, so the inside of the house now is the hot region, and the outside of the house is the cold region, okay? And what we're trying to do is get heat to go into the house. Okay, that's the purpose of the heat pump. So again, the schematic looks exactly the same as the refrigerator. It's just that what we're using this device for is to bring heat into the hot region, okay? So remember, we have this idea of a coefficient of performance, and it's what you have to, it's the ratio, of what you get out divided by what you put in, okay? So for a heat pump, what you're trying to get out is QH. So that goes on top. What you have to put in is W. So the coefficient of performance for a heat pump would be defined as QH divided by W. Now, of course, we can rewrite this. I showed you earlier that the work can be thought of as QH minus QL. So you can make that replacement here and get the result that for a heat pump, the coefficient of performance is QH divided by QH minus QL. Okay? So that's going to be it for this video. We'll end it here and continue our discussion of heat engines, refrigerators, and things like this in the next one. So until then, I'll see you later. Take care.